When determining voltage drop in electrical circuits, it is essential to use the actual run distance of the conductors. This means measuring the physical length of the wire as it is installed, following its path through walls, ceilings, and any other structures. Using a straight line, or as the crow flies, distance will result in an inaccurate calculation and could lead to undervoltage issues at the load. Voltage drop is the decrease in voltage that occurs along a conductor due to its impedance. Impedance is the opposition to the flow of alternating current and includes both resistance and reactance. Resistance is the opposition to current flow due to the material and size of the conductor, while reactance is the opposition to current flow due to the inductance and capacitance of the conductor. The longer the conductor, the greater the impedance, and therefore the greater the voltage drop. The formula for calculating voltage drop is voltage drop equals current times impedance. In alternating current circuits, the impedance is a complex number that takes into account both resistance and reactance. However, for many practical applications, the inductive reactance can be ignored, and the voltage drop can be approximated as voltage drop equals current times resistance. The resistance of a conductor depends on its material, length, and cross-sectional area. The resistance increases with increasing length and decreases with increasing cross-sectional area. The National Electrical Code, or NEC, provides tables that list the resistance of different types of conductors per unit length. For example, NEC Chapter 9, Table 8 provides the resistance and reactance for alternating current cables. To calculate the voltage drop, you need to determine the current flowing through the conductor, the resistance of the conductor, and the length of the conductor. The current can be determined by dividing the power consumed by the load by the voltage. The resistance can be determined using the NEC tables or by using the formula resistance equals resistivity times length divided by area. The length is the actual run distance of the conductor. Once you have determined the current, resistance, and length, you can calculate the voltage drop using the formula voltage drop equals current times resistance times length. The voltage drop should be within acceptable limits. The NEC recommends that the voltage drop should not exceed 3% for branch circuits and 5% for feeders. If the voltage drop exceeds these limits, you need to increase the size of the conductor or reduce the length of the run. Several factors influence the selection of the appropriate wire size for a particular application. Firstly, ampacity, which refers to the current carrying capacity of a conductor, must be considered. The ampacity is the maximum amount of current that a conductor can safely carry without exceeding its temperature rating. The NEC provides tables that list the ampacity of different types of conductors based on their size, insulation type, and installation conditions. The ampacity of a conductor decreases as its temperature increases. Therefore, it is important to select a conductor with an ampacity that is sufficient to carry the expected load current under the worst-case temperature conditions. Secondly, voltage drop must be taken into account. As previously discussed, voltage drop is the decrease in voltage that occurs along a conductor due to its impedance. Excessive voltage drop can cause equipment to malfunction or not operate properly. The NEC recommends that the voltage drop should not exceed 3% for branch circuits and 5% for feeders. Thirdly, the type of load must be considered. Some loads, such as motors and transformers, require a higher starting current than their normal operating current. This starting current can cause a significant voltage drop, which can prevent the equipment from starting properly. To mitigate this issue, it may be necessary to use a larger conductor or to use a voltage drop compensation device. Fourthly, the installation conditions must be considered. The ampacity of a conductor is affected by the ambient temperature, the number of conductors in a raceway or cable, and the presence of thermal insulation. The NEC provides adjustment factors that must be applied to the ampacity of a conductor to account for these factors. Fifthly, the cost of the conductor must be considered. Larger conductors are more expensive than smaller conductors. Therefore, it is important to select a conductor that is large enough to meet the requirements of the application, but not so large that it is unnecessarily expensive. In addition to these factors, other considerations may also be relevant, such as the mechanical strength of the conductor, the resistance of the conductor to corrosion, and the availability of the conductor. By carefully considering all of these factors, you can select the appropriate wire size for a particular application. To accurately measure the actual run distance, use a measuring tape or a laser distance meter. Ensure the measurement follows the exact path the wire will take. Account for any bends, turns, or vertical runs. For complex installations, it might be helpful to use a fish tape to simulate the wire path and then measure the fish tape. Remember, underestimating the distance can lead to significant errors in voltage drop calculations, potentially causing equipment malfunction or safety hazards. When calculating voltage drop, always refer to the latest edition of the National Electrical Code for the most up-to-date requirements and guidelines. The NEC provides specific tables and formulas for calculating voltage drop based on conductor type, size, and installation conditions. Understanding and applying these guidelines is crucial for ensuring safe and efficient electrical installations. The impedance of a conductor is dependent on several factors, including the material of the conductor, its cross-sectional area, the frequency of the current flowing through it, and the temperature of the conductor. The material of the conductor affects its resistivity, which is a measure of how strongly the material opposes the flow of electric current. Copper and aluminum are the most commonly used conductors in electrical wiring due to their low resistivity. The cross-sectional area of the conductor affects its resistance. A larger cross-sectional area provides more space for electrons to flow, resulting in lower resistance. The frequency of the current flowing through the conductor affects its impedance. At higher frequencies, the inductive reactance of the conductor becomes more significant, increasing the impedance. The temperature of the conductor also affects its impedance. As the temperature increases, the resistance of the conductor increases, which in turn increases the impedance. To minimize voltage drop, it is important to select conductors with low resistivity, large cross-sectional area, and to keep the conductors as short as possible. It is also important to minimize the operating temperature of the conductors by ensuring adequate ventilation and avoiding overloading the circuits. Voltage drop can also be reduced by using a higher voltage. For example, transmitting power at 480 volts instead of 208 volts will reduce the current required to deliver the same amount of power, which in turn will reduce the voltage drop. However, using a higher voltage requires careful consideration of safety and code requirements. When calculating voltage drop in three-phase circuits, the calculations are slightly different than in single-phase circuits. In a three-phase circuit, the voltage drop is calculated as voltage drop equals the square root of 3 times the current times the impedance times the length. The square root of 3 factor accounts for the fact that the voltage between any two phases in a three-phase system is the square root of 3 times the voltage between one phase and neutral. Another important consideration when calculating voltage drop is the type of load being served. Some loads, such as motors and transformers, have a high inrush current when they are first energized. This inrush current can cause a significant voltage drop, which can prevent the equipment from starting properly. To mitigate this issue, it may be necessary to use a larger conductor or to use a voltage drop compensation device. Voltage drop compensation devices, such as autotransformers or electronic voltage regulators, can be used to boost the voltage at the load end of the circuit, compensating for the voltage drop. These devices are typically used in applications where voltage drop is a significant concern, such as in long feeder runs or in circuits serving sensitive electronic equipment. In summary, accurately calculating voltage drop is crucial for ensuring safe and efficient electrical installations. Always use the actual run distance of the conductors, consider all relevant factors such as conductor type, size, and installation conditions, and refer to the latest edition of the National Electrical Code for guidance. Furthermore, always double-check calculations and consult with a qualified electrician if you have any doubts or concerns. Firstly, consider the ambient temperature in which the conductors will be installed. Higher ambient temperatures can reduce the ampacity of conductors, requiring the use of larger conductors to maintain the same current carrying capacity. Secondly, take into account the number of current carrying conductors in a raceway or cable. When multiple conductors are bundled together, their heat dissipation is reduced, which can also reduce their ampacity. The NEC provides adjustment factors for directing the ampacity of conductors based on the number of conductors in a raceway or cable. Thirdly, consider the type of insulation used on the conductors. Different types of insulation have different temperature ratings, which affect the ampacity of the conductors. The NEC provides tables that list the ampacity of conductors based on their insulation type and temperature rating. Fourthly, take into account any voltage drop requirements. As previously discussed, excessive voltage drop can cause equipment to malfunction or not operate properly. It is important to select conductors that are large enough to minimize voltage drop and ensure that the equipment receives the required voltage. Fifthly, consider any future expansion plans. If you anticipate the need to add more load to the circuit in the future, it is wise to select conductors that are large enough to accommodate the additional load. This will avoid the need to replace the conductors later on. Sixthly, consider the cost of the conductors. Larger conductors are more expensive than smaller conductors. Therefore, it is important to balance the need for adequate ampacity and voltage drop performance with the cost of the conductors. Seventhly, consider the availability of the conductors. Some conductor sizes and types may be more readily available than others. It is important to select conductors that are readily available to avoid delays in the installation process. Eighthly, consider any code requirements. The NEC and other applicable codes may have specific requirements for conductor sizing and installation. It is important to comply with all applicable code requirements to ensure the safety and legality of the installation. Finally, always consult with a qualified electrician to ensure that the conductors are properly sized and installed. A qualified electrician can assess the specific requirements of the application and recommend the appropriate conductors. Remember that using the actual run distance is paramount for accurate voltage drop calculations. Overlooking this detail can lead to incorrect wire sizing and potential problems in the electrical system.